finally we get to the explanation of this effect by the man himself, finally meeting him, Einstein. So let's have a look at our setup. We've got our anode surface of the metal here, and we're shining light on it. Now for this particular metal, I'm going to say the work function, which is how strongly these electrons are connected to the metal, is equal to 2.2 electron volts. So that is how much energy you need to give one of these electrons before it will be ejected and become a photoelectron. And I've got two different light sources. So this is what Einstein said. Instead of thinking what everyone else thought, light was a wave, even Planck came up with the idea of quantization, but he didn't really believe it. He still thought light was a wave. Einstein said, well, let's actually, Planck's observations actually mathematically work. Let's assume they're correct. That light is not a wave, but it is particles, little particles, and he called them photons. So here are the photons, and I've got a red light here, so red photons, and a blue light over here, so blue photons. Now what Planck said was that the energy in these photons is equal to HF, which is Planck's constant times the frequency of the photon. Now that's going to give us an answer in joules, but because we have a work function in electron volts here, I'm just going to skip a step and say that, and I've already done this calculation, that these are red photons given their frequency, which is, I've just picked a red frequency of light. They have an energy of 1.77 electron volts. So each of these photons carries 1.77 electron volts of energy. And likewise, picking a blue frequency of light, I have calculated that these photons carry 3.11 electron volts. So they're high energy photons. So what Einstein said was essentially it's an all or nothing interaction between a photon and an electron. The photon can kind of just, it can miss, it can be absorbed maybe in the surface of the metal, or it can be reflected, bounce off the metal, or if it's absorbed, it's 100% absorbed by the electron. All of the energy in this photon is transferred to the electron. Okay, you can't transfer half of that energy or 3/4 of that energy to the electron. It's all or nothing. And if it hits the electron, it's going to give all of that energy to it. So let's look at it hitting the electron. Remember, this photon has 1.77 electron volts of energy. So it comes down, hits the electron, is completely absorbed. What happens? Well, this electron is connected by a bond that has a strength of 2.2 electron volts. 1.77 is not enough energy to break that bond. So that photon gets absorbed, nothing happens. The next one comes down, photon gets absorbed, nothing happens. So where's the energy going? Well, actually, it's kind of going to vibrations of the atoms in this metal, kind of just heat vibrations, heating up that metal. Next one comes down, absorbed, still not enough energy to break that bond, nothing happens. And you could shine this light for hours and hours and hours, but individually each of these photons does not have enough energy to break that bond, so you'll never get a photoelectron ejected. Put those back. Let's see if I make the light brighter. What does it mean to make the light brighter? It just means I'm sending down more photons. So before, let's say that was a very weak light. Now we're turning up the brightness, much more intense light, which means much more photons coming down. But individually, those photons are still the same photons. They still carry only 1.77 electron volts, which is not enough to break this bond ever. So you'll never get a photoelectron using this frequency or this wavelength of light with this particular anode, which has the work function of 2.2 electron volts. You could have a different anode. Maybe the work function would be 1.5 electron volts. Then that would be enough to break it, but not this anode. So I changed my frequency of light, and now I use blue light. And these blue photons carry an energy of 3.11 electron volts. Send one down, it gets absorbed, And this 3.11 is bigger than 2.2. So what happens? All that energy, so the photon gets absorbed, and the bond is broken, and the electron is now a photoelectron. It gets ejected from the surface of the anode, and now it has some kinetic energy. How much kinetic energy does it have? It should be hopefully pretty easy to see that it's whatever is left over. Okay, so 3.11 electron volts came in and was absorbed by the electron. It needed 2.2 electron volts to break the bond. Whatever's left is the kinetic energy that this electron has as it flies away from the surface. So we can get the formula that I've got in the notes there, which tells us that the K max, the maximum kinetic energy, is equal to the energy of the incoming photon, which is HF, minus the energy, or minus the work function, so minus the energy required to break the bond. And that would give us the Kmax of the photoelectron as it flies away. And just important to note that you need these three, they're all values of energy, so they all need to be in the same unit. Okay, so if I have an incoming photon energy of 3.11 electron volts and a phi of 2.22 electron volts, for this example, it's going to give me 0.11 minus 2.2 equals 0.91 electron volts. Oh, you would. Which is going to be my kinetic energy left over. It gives me a Kmax in electron volts. I could also have an incoming photon energy in joules, and then I could have a work function in joules. I could convert that 2.2 electron volts to a value in joules, and then I get a Kmax in joules. But you can't mix and match. You can't do, H times F gives me an answer in joules, and then I'm going to subtract 2.2 electron volts, and that doesn't make sense to do that. Okay, it's algebra. You have to subtract or add like terms. These have to be in the same unit, and that is that.